we're going to look at a specific application of concentration and time for chemical kinetics, and that's half-life, which means just what it says. How long until you get to half of what you started with? And we're going to look at it for first and second order equations. And so you have to start off with the basic mathematical relationship for both. So for first order, this is the equation we're going to start with, and then we'll manipulate it. And then this was the equation for second order. Now, as a reminder from my students, I don't require you to show a derivation for a mathematical equation, but it's important to see where they come from. So we'll start with first order. Since we're talking about half-life, that's what our final time is. How long did it take until we had half the material? And so I'll make that simple substitution into the equation. Then, since it's half-life, I'm going to plug in for the concentration at that time, half of the initial. Now, it doesn't look like it helps any, but we're not done yet. What I'll do next is solve for minus kt 1/2. So I'll move that over to the other side. And then that means I have to subtract this from both sides. And so I get this on the bottom in the middle. And it doesn't look like it helped any, does it? Well, we're not done. All right, let's look at this. There's a property of logs that we can use. And if you look over to the left on the bottom, if you take the natural log of x minus the natural log of y, it's really the natural log of x divided by y. So we're going to use that to our advantage. Just as a side note, if you've ever wondered how people who know how to use slide rules can do calculations so quickly, that's because when we're multiplying and dividing, people using slide rules are adding and subtracting. So let's make that substitution in the bottom middle, and then we get what's up on the top. Now I can simplify that. You see, I have the initial concentration times 2 over the initial concentration. So let's get rid of that. And almost there. Let's solve for that t 1/2 because we're looking for half-life. And this is the equation for half-life for a first-order reaction. Let's go on to second order, and then I'll put both of them up and we'll talk about them. So for second order, I'll do the same thing I did initially. That is, time is going to be t 1/2. So I'll substitute that in. And then, at t 1/2, we have half of the initial concentration. So that's being substituted in for 1 over the concentration at t 1/2, which means I take the reciprocal of it. That's why I get 2 over the initial concentration. And then, since we're working our way to a formula that says t 1/2 equals blah, I will subtract from both sides the 1 over the initial concentration and then flip the equation around. That's what I get on the upper right. Well, on the upper right, the denominators are the same, so just take 2 minus 1, and we get that. And then I'll isolate t 1/2, And that's the mathematical formula for second order half-life. Okay, so here are the two equations that we derived. One thing that you have to get, even if you don't memorize these formulas, you have to understand that first order half-life is independent of concentration. See, it's just natural log of 2 over k, whereas second order has concentration in it. The way that I conceptually remember that is if I have a first order reaction, it's one particle doing something all by its lonesome. So whether I have 100 or 1,000,000 particles in a certain volume, it doesn't matter. That's radioactive decay. Second order. For anything to happen, these two particles have to come together. So if I have a certain volume, if I have 100, there's a certain probability of the particles smacking into each other and reacting. Whereas if I put 1,000,000 particles in that same region of space, there's a higher probability that they're going to react, which means, since in the denominator, that means the time decreases. Now, honestly, you don't have to memorize these formula. The first order one is useful if you're doing a lot with radioactive decay, sure. But you can derive these two formula from the initial equations. You don't have to walk through everything that we did. It's just if you memorize, say for first order, the basic relationship on the upper right, you can quickly plug things in and solve for whatever you need, whether or not it's half-life. Same idea for the second order equation, the one on the bottom right. If you can't remember the half-life formula, you go back to the basic formula because you have to know those two on the right side. So bottom line, if you're having trouble remembering the half-life formula, because, it's tough to remember some of these things for an exam situation, then don't. Remember the concentration and time relationships, and then solve them whether they're half-life or not. It doesn't matter. Now for those half-life equations, those are specific to half-life. So if you're talking about, say, like you have a 10th or a 14th remaining, you can't use those equations the way they've been written.